So in the last lecture we started our discussion on the molecular ion H2 plus. And we determined the Hamiltonian for this system. So a quick recap is we have two nuclei separated by some distance r, and we have an electron. So the position vector of this nucleus was given by r over 2. The position vector of this nucleus is given by minus r over 2, and the position vector of the electron is given by r. And we defined two states. One state was ket 1, which basically means that the electron is primarily associated with one electron, and ket 2, which means that the electron is primarily associated with the second electron. Later we label these nuclei as A and B. So if you would like to gain more information, or you would like to gain a better understanding of these states, ket 1 and ket 2. Ket 1 is an atomic orbital. It's the ground state of a single hydrogen atom in which this nucleus is far away. And if you represent this in the position representation, in the ground state, this is simply 1 over pi a naught cube under root e raised to power minus this distance, which is r plus r by 2 over a naught. Okay? So this is what ket 1 really means. It's an atomic orbital in which the electron is associated with nucleus A. It's an atomic orbital. Likewise, this state has a wave function 1 over pi a naught cube. A naught is the Bohr radius once again, e raised to power minus r by 2 over a naught. So this is what ket 1 and ket 2 means. And we also know what the Hamiltonian is. The Hamiltonian is a single electron system. It's p square over 2m minus e square over 4 pi epsilon naught r minus this distance, which is r plus r over 2 minus e square over 4 pi epsilon naught r minus r over 2, right? So this represents the interaction of an electron with each nucleus plus an electrostatic repulsion between the two nuclei. So this is the Hamiltonian. And if we would like to diagonalize this Hamiltonian, we found out that the eigenstates for this Hamiltonian are combinations of ket 1 and ket 2. And that, remember, ket 1 is not orthogonal to ket 2. These are not orthogonal states, because if you consider ket 1, it's this electron belonging to this nucleus. Ket 2 is this electron belonging to this nucleus. Since the nuclei are identical, the electron is just the same. Both of these states have the same energy, E1 minus 13.6 electron volts. So the eigenstates are degenerate. The eigenvalues are not distinct. So ket 1 and ket 2 are not orthogonal vectors. So now if you would like to calculate, we found out that the two eigenstates are given by the combination of 1 and 2. So this is one eigenstate, and we need to diagonalize this as well. So, normalize this. So when we normalize this, we obtain this normalization factor 1 plus 1, the overlap of 1 with 2. This is not 0. if these particles are really far apart, the nuclei are really far apart, then this overlap integral goes to 0 and we're left with ket1 plus ket2 current. So this is one eigenstate. The other eigenstate is ket1 minus ket2 over under root 2 under root 1 minus 1 2. Alright, so we have linear superposition of states which are eigenstates of this Hamiltonian. One of these states, let's label this state as phi b, and let's label this state as phi a. This b means that we have what is called a bonding molecular orbital, and this a stands for an anti-bonding molecular orbital. This is a linear combination of atomic orbitals. In the parlance of chemistry, this kind of orbital is called an LCAO, a linear combination of atomic orbitals. It's a molecular orbital. You must have studied molecular orbitals in basic chemistry. So this is a bonding molecular orbital and this is an anti-bonding molecular orbital. Okay? Now what we would like to do, we would like to find out the energies associated with these molecular orbitals. Okay? We are really interested in finding the Hamiltonian is going to be diagonal in the basis of these bonding and anti-bonding orbitals. So first of all, we would like to find out this energy. This is the energy of the molecule in the bonding state. Okay. And why do we call it the bonding? We'll find out when we once computed the energies. So if you compute this, the bonding state is given by this, so I'm left with 1/2 1 plus O. So the overlap integral ket1 inner product, I'm calling it O. 1 plus 2, and then I have my Hamiltonian 1 plus 2. Now this is what I would like to calculate. Okay, so this really means 1, 2, 1 plus O. Now I write this in the following fashion. I have 1 H1 plus ket bra2 H2. Since these are identical, so I put in a 2 here, plus 1 H2 plus 2 H1, but since we've already known that the off diagonal elements are equal in the Hamiltonian and the diagonal elements are also equal, so I'm left with this situation. So I'm left with 1 plus the overlap integral, and I need to calculate H11 plus H12. Okay? So these are just matrix elements of the Hamiltonian in the basis ket1, in the ket1, ket2 basis. Likewise, the anti-bonding energy EA can also be computed. If I just replace phi b with phi a, I put in ket1 minus ket2 here, ket1 minus ket2 here, I replace this plus with a minus sign, I get 1 over 1 minus O H11 minus H12. So the next step is I would like to calculate what these values are. Right? I need to calculate this and I need to calculate this. So I can find out the energies of the bonding and the anti-bonding states. Alright, so I know what the Hamiltonian is. So let's first calculate this term. This term H11 is given by. Now I have to sandwich the Hamiltonian between the state 1. Now if I look at the first two terms in the Hamiltonian, from these first two terms, Ket1 is an atomic orbital and it's an eigenstate on the first two terms because the first two terms just represent the atomic Hamiltonian. These two terms represent the atomic Hamiltonian when the electron is associated with this nucleus. So this is just H atom 1 when the electron is with nucleus 1. So if I sandwich this between Ket1, I will just get the energy of the ground state of the hydrogen atom, which is minus 13.6 electron volts. So this will give me minus E1 plus E1. This is a negative number, minus 13.6 electron volts. Now I need to sandwich the second term, which is minus E square over 4 pi epsilon naught. I have Ket1, 1 over R minus R by 2, Ket1. Plus, now capital R is a constant. We are expressing in terms of small r, so capital R is a constant. So the last term is just E square over 4 pi epsilon naught R Ket1 with itself. 1 is normalized, so I could have 1 here. So this is my H11. Now if you look at this term, this is just the ground state energy of a single electron with a single nucleus. This term, what does this term represent over here? Let's call this term some C. C, it's constant C. What does this term physically represent? This term represents an electron is close to nucleus 1, right? This is Ket1, but it is seeing an attraction by the nucleus number 2, by the nucleus B. An electron is close to nucleus A. That's why we have this Ket1 over here, but it's seeing attraction, it's being attracted to nucleus B. So this is the Coulombic attraction between an electron which is close to one nucleus, but the attraction seen by the other nucleus. So this is a Coulombic term and it's negative. This really means, this really is equal to minus E square over 4 pi epsilon naught d cube r r1 modulus square 1 over r minus r by 2. This is what this term actually represents. If you would like to compute this term, this is what you need to do. Right? So this is a Coulombic term. It shows the attraction of an electron that's close to this nucleus, that's basically attached to this nucleus, but it's seeing an attraction by the other nucleus. Okay? And it's negative, so it's an attraction. This represents a positive term. Let's call it, say, some F. So if I would like to calculate H22, I will still get an E1 here. I will get 2 here, 2 here. This will be R plus capital R over 2. So it's still an electron that is attached to nucleus B, but seeing attraction by nucleus 1. Due to symmetry of the problem, it's going to be the same term, and this is nevertheless the same. So this thing equals this thing. So what I've done now is I've calculated H11, and H11 is, I label this as E1 plus C plus F. Okay. Each one of these is this is an integral, right? So this is negative, negative, and a positive number. Alright. Now let's calculate H12. Okay, because I need this energy and I need this energy. So H12 is calculated similarly. Okay, let's calculate it. One. Now I have the H atom 1, 2 plus or minus E square 4 pi epsilon naught 1 over R minus capital R by 2 plus E square 4 pi epsilon naught R 1 2. So this is the off diagonal term of the Hamiltonian in the ket 1 ket 2 basis. Now this is an eigenstate of this with energy E1, so I get E1, but the inner product 1 with 2 is called O, the overlap integral. Now this thing is now a term which is a Coulombic term. So an electron here, if you look at this term represents a Coulombic, this is a Coulombic term over here. Now this term over here is different from this term. So let's label this term, say, some D. And once again I have an F with an O. Okay. Alright, this looks fine. This we've defined as C over here. This is this term. And this is a term which is again a kind of overlap integral. It's an overlap between an electron being attached to nucleus A and an electron being attached to nucleus 2, to nucleus B, and then there is this distance in between. So it's kind of an overlapping integral. Now you have these terms over here, and if I would like to find out the energy of the bonded state, EB, the energy of the bonded state is given by this. So I have 1 plus O, then I have E1 plus C plus F, I have E1O plus D plus FO. And when I evaluate this, I get E1 plus F plus C plus D O. This is the energy of the bonding orbit, bonding molecular orbit. Okay. Likewise, the energy of the anti-bonding orbital will be given by E1 plus F plus C minus D over 1 minus O. G.
So, in the term that we labeled F, so we imply that they are kept in the block active.
Right, so there is 1 here.
Yes, and so in this case,
Yes, we also have this at 1, 2. R, capital R is a constant vector as far as the electronic coordinates are concerned. So it can be pulled out of integral.
right. So how do we have an F here now?
Because this is defined as F, right? This thing is F. This thing is the same as this thing over here.
This is the constant.
Yes, it's R, capital R could be a parameter, but it does not depend upon the electronic coordinates. It depends upon the internuclear distance. And when we are taking integrals, we are integrating over the electronic coordinates because we are dealing with electronic wave functions, right? So this is EA, this is EB. Now if you notice, this term C is negative, this is a negative term over here, and D, this term is also negative, and there's a positive sign over here. So this is negative, this is also negative, and there's a positive sign over here. What this shows us is that EB is less than EA. Now how do you convince yourself of this? What you need to do is you would need to plug in the values for the atomic orbitals for the 1s state. You need to plug in these values over here, and you can find out what these energies are going to be. This is question number 1 of your second homework. But it's clearly evident from the expression that I've written that EB is going to be less than EA because you have a negative terms here and they are being added. So you have more negative and there's a bigger denominator, so you have more negative here, you have less negative here. So this EB is smaller than EA. So what you really have is a separation between the bonded state, the bonded molecular state, and the anti-bonding molecular state. And you can quickly find out what this difference is going to be. Okay, it's just going to be the difference of these terms. G.
So O is a positive term, but it is also less than 1.
Yes. Alright, so now we have an energy separation between the bonding molecular orbital and the anti-bonding molecule. So if you just have one electron, as you have in the H2 ion, that single electron will go to this state. And its spin is unimportant because there is no restraint implied by the symmetrization postulate because it's just one electron. It's not seeing any other electron. So the spin could be up or down, it doesn't really matter. Now let's get a physical feel of what the wave functions are going to look like. So you have two wave functions over here. This is the bonding wave function, this is the anti-bonding wave function. Now if you just plot ket1 in the position space, now ket1 in the position space I've written over there. So ket1 in the position space, it's just the 1s orbital. The 1s orbital which peaks at minus r by 2. So it peaks over here, it is minus r by 2 over here. The 1s orbital, if you plot the function over here, it just decays exponentially, right? Like this. Now if you plot this wave function, which is the other atomic orbital. It's the second on the top over there. This peaks at r small r equals plus r by 2. It's just the 1s orbital. It's decaying like a 1s orbital. It has an exponential decay. It's an s orbital, nothing else. But with the position being shifted, the wave function is centered at the location of nucleus A. This wave function is centered at the location of nucleus B. Now if you plot the bonding molecular orbital wave function for the bonding state, phi b. Now if I don't put ket, it means the wave function. I'm representing this wave function, the position space. If I plot this, and I have the vector r over here, this is r, the distance from the node between the two nuclei, the function that I will obtain looks like this. And if I plot the probability density, it's just going to be the modulus squared of this. So there's a single electron. The highest probability is that the electron is attached to one nucleus or the other nucleus, and it's symmetric about this nodal plane. And there is also a finite probability that the electron is in between the two nuclei. Okay? So this is the probability density for the electron in the bonded state, in the bonded molecular orbital, bonding molecular orbital. Now let's plot the wave function in the anti-bonding molecular orbital. We know that this is lower in energy. This configuration is lower in energy because we've just calculated it. In the anti-bonding molecular orbital, it's just the difference between, you have to take the difference between ket 1 and ket 2. So one is this state, other is this state. So ket 2 is negative. You have ket 1 minus ket 2. Now if you add the two, you get the wave function for the anti-bonding state. And that wave function looks like this. And now if you take the probability, which means that you take the probability density, you square this, you get this. This is phi a modulus squared. So now you have zero probability for finding the electron in between the two nuclei. Okay, in the nodal plane. The electron, if it is close to just one nucleus, then what you have is an electron close to a proton. Nucleus is a proton here, because we're talking about hydrogen. You have one atom and one proton. It's a charged species. This has higher energy. So if the electron associates itself with only one nucleus, you have a higher energy. If the electron is in between, the electron is being pulled. It's by each nucleus. It's under the attractive influence of each nucleus. This is a lower energy state. So the electron would actually like to be in between the two nuclei. Look, here the probability density at the nodal plane is 0. Here the probability density is finite. So the electron is a greater propensity of finding the electron in between the two nuclei. And this actually bonds the two nuclei together. That's why it's called a bonding molecular orbital. This is a low energy configuration. It bonds the two nuclei together. Alright? So this is the simple description of a hydrogen molecular ion in which one electron has been stripped off. So there is one electron under the influence of two electrons. And there is no concept of electron interactions here because it's just one electron. Now based upon this picture, we can build up the picture for hydrogen molecule. There is no exchange interaction over here because it's just one electron. There are no correlations involved. So let's talk about an electron. By the way, if you were to plot the energies, so this is, if I take the variable, the parameter R, and I plotted the energies for EA and EB, this is the energy for EA, and this is the energy for EB. The energy for EB is lower than the energy for EA, and this separation over here is for the equilibrium bond length. You can plot these energies in fact. You can find out what these energies are going to be because you can explicitly determine these terms. You can determine this integral, this integral, this integral. And this is actually one question on the second homework. I would like you to plot these energies. And this, by the way, this is minus 13.6 electron volts, which is the energy of a single electron. When R is really large, it means that the two nuclei are independent. So the energy of the system is going to be minus 13.6 electron volt. So this energy is minus 13.6 electron volt. If the two nuclei come close together, so you're moving towards the origin of this graph, then the energy for the bonding molecular orbital state decreases. So the electron prefers to be in the bonding molecular orbital state. And it prefers to take up the equilibrium bond length. And this is actually the binding energy of the molecular line. This is called the binding energy. And its value is between 1 and 2 electron volts. Now with this backdrop, I would like to talk about the hydrogen molecule. And I would like to introduce the exchange interaction there, because the exchange interaction is at the heart of magnetism. Remember, first we studied a helium atom. And in the helium atom, we noticed that there was exchange interaction. And we noticed that we have for the ground state, this is just a singlet. For the first excited state, we had a triplet, and then we had a singlet, and triplet was lower in energy, and this separation was 2J, and this was an exchange integral. This is what we calculated for the helium atom. Now we would like to precisely do the same kind of calculation for the hydrogen molecule. So first we studied intra-atomic exchange interactions. Now we are stepping into the domain of chemistry in which atoms are coming together and making molecules. And it was when Lewis presented the idea of the chemical bond, for which he got the Nobel Prize as well. Does the spin have any role to play over there? Is magnetism important for bond formation? Are spins important? Yes, they are important. And the hydrogen molecule vividly demonstrates this effect. Okay, so now we're going to look at the hydrogen molecule. It's going to be a long, tedious calculation, so I'm going to skip many steps, but I'll give you the essential ideas. यहाँ तक कुछ सवाल? Please submit your homeworks in the next few hours or so. Okay, now let's make a diagrammatic representation of the hydrogen molecule. You see, we have two nuclei. This is R by 2. Once again, this is minus R by 2. This is our origin, which we set by our own choice. This is nucleus A. This is nucleus B. And now we have two electrons with position vectors R1 and R2. So this is our basic kind of diagram over here. Alright, now what I would like to do, first of all, I would like to propose a ground state for this molecule. Now you have two electrons. What is the quantum state of those two electrons? Okay, so I would like to propose a trial quantum state. Now, in the atomic orbital, in the independent electron treatment, which is the molecular ion, the electron would like to be in the bonding molecular orbital state. Each electron. So each electron would like to be in the phi d state. Okay. So now I propose that the ground state for the electrons is the first electron is in the bonded state phi b at position vector r1, and the second electron is also in the bonding molecular orbital state, position vector r2. So this is the first electron, the second electron. Okay. So I'm just taking ideas from the molecular ion and trying to graft them onto the molecule and trying to come up with a trial solution. Alright. Now, is this even or odd under exchange? I would like to have a spatial quantum state to be either even or odd, and I would like to combine it with the spin configuration which renders the overall quantum state to be odd. Is this even or odd? अगर मैं यहाँ पे phi b r2 ले आऊँ और phi b r1 ले आऊँ, it's not the same because the first electron is now, if I swap the variables, r2 comes here and r1 comes, it's not the same state because this is the first electron, this is the second electron. So what I need to do, I need to form combinations. I will form, if I have this combination, remember there's a tensor product in between, the ordering is important. So if I form this combination, phi b r1, and then if I swap the variables, I interchange r1 and r2, which means I take one electron, put it onto the position of the other one, and take the other electron, put it onto the position of the other one, then I get a symmetric wave function. So I also have to normalize this. Now this can combine with a singlet wave function, singlet spin wave function. This can combine with 1 over under root 2 alpha beta minus beta alpha. This will, if I interchange both variables, the positional variables and the spin variables at the same time, then I will get a quantum state that's negative of the origin, which is required for electrons. So this is my candidate ground state, in which I have a superposition of the bonding molecular orbital states for each electron. Right? Now what I would like to do is, each one of these states I know is given over there. Phi b is written over here. This is phi b for one electron, this is phi a. So phi b for one electron is parameterized by the vectors r1 and r2. So if I replace phi b r1 by 1 over under root 2 1 plus O 1 R1 plus 2 R1. So I can make this replacement over here. So wherever this occurs in here, I can put this in. What does this mean? This means that I have an electron at position R1. This term means that this electron at position R1 is attached to nucleus 1. This means that the electron at position R1 is attached to nucleus 2. Okay? Let me repeat this. I have now two variables, R1 and R2, because I have two electrons. Previously I just had one variable which I called small r. Now I have two variables, small r1 and small r2. See? These two variables appear here. Now what I would like to do, I would like to expand these molecular orbitals in terms of atomic orbitals. These are molecular bonding molecular orbitals, so I would like to expand each linear combination in terms of the atomic orbitals itself. And what kind of expansion does this mean? This means that a bonding state has to be written in this fashion. And if I have a 2 over here, this just means that I put a 2 over here. If I just have R1 here, it means that the electron is at position R1. And if there is a 1 here, it's attached to nucleus A. And if R1 has a 2 here, it means that this electron is attached to nucleus B. Right. This is what this prescription means. Now I insert all of the values over here. I put in everything in here. Okay. The final state that I get, the ground state, is the following. Now what I would like to do, I would like to express this in the position representation, in the R representation. So I will, okay, right? So I'm just going to write down a result over here. What I have is so I have some normalization constant A. Alright, and on top of that I have terms like this. I get terms like this. I get 1 R1 plus 2 R1 1 R2 plus 2 R2. So this is this direct product. Then I have 1 R2 plus 2 R2, and then I have this 1 R1 plus 2 R1. Right? So then I multiply all of this together. I've just replaced each one of these bonded states by the linear combination of the atomic orbitals, right? Here's what I've done over here. Nothing special. At the end, what I get is a state. Now I do some simplifications over here by noticing that the electrons are independent particles and they are indistinguishable particles. There are lots of simplifications that you need to do And the final state that we obtain is slightly complicated in writing it down, is the following. This calculation was done in 1927 by Heitler and London. Final state that we get in quantum notation, in the state notation, is the following: 1 over under root 2 1 plus s one R1 2 R2 plus 2 R1 1 R2 1 over under root 2 alpha beta minus beta alpha, okay, plus 1 over under root 2 1 plus s one R2 plus 2 R1 2 R2 alpha beta minus beta. So this is a state that we obtained. After some manipulations and after some simplification, I would urge you to do this on your own, okay? Because the experience will be illuminating. Now let's look at this ground state. So we started off with a symmetric spatial state combined with a singlet spin state. And then when we put in the atomic orbitals, this is the final stage that we set for ourselves. Now look at this second term over here. The second term. This is the second term. This is the first term. We don't need to consider the spin state for a minute. Look at this second term over here. I've just done algebra and I've use the symmetry of the state to identify terms that are equal to one another. What does this mean? Look at this term. The first electron, this is the first electron, second electron. First electron is at position R1 and connected to nucleus 1. The second electron is at position R2 and also connected to nucleus 1. So both the electrons are connected to one nucleus. It's kind of strange. And there's no electron with the other nucleus. So you have one bare proton and one nucleus that has two electrons. So this really means that you have a situation like this. You have one hydrogen ion which is negatively charged because it has two electrons. And this represents a proton, a nucleus, just a nucleus, without an electron close to it. So in bond language, this is called an ionic bond. Both of the electrons migrates to one nucleus. Likewise, this represents the first electron, the second electron. The first electron is at position R1 and is connected to nucleus B, second nucleus. The second electron is at a different position R2, but it's associated with nucleus B. So this represents H plus H minus. So this term represents both the electrons have migrated to nucleus B, and this represents that both electrons have migrated to nucleus A. So this represents an ionic term, an ionic bond, in other words. Okay? Now in an ionic bond, you have an anion, negatively charged ion, and a positively charged ion. So it's a high energy configuration. So what we're looking at is the quantum mechanics of bond formation here. So this is a high energy configuration. Let's look at this term over here. The first term. In the first term, first electron, second electron. First electron is at position R1 and associated with nucleus A. The second electron position R2 associated with nucleus B. So there is sharing of the electrons. Each nucleus gets half of the pie, gets half of the share of electrons. First electron, position R1, attached to nucleus 2. Second electron, position R2, attached to nucleus 1. So this again represents sharing of electrons. So this represents a covalent term. And this is called a covalent bond. Okay, with the sharing of electrons. Now the approximation made by Heitler and London was that they ignored this term in calculating. So what we're interested in is calculating the energies. Right? We're interested in calculating energies. So Heitler and London in their paper, this is called the Heitler and London approximation. They ignored the high energy ionic terms, and they proposed that the correlated electron quantum state in the ground state for the hydrogen molecule could either be the symmetric or the singlet ground state. The singlet state, which is given by the first of these terms. So it could be 1 over under root 2, 1 plus S, one R1, 2 R2, plus 2 R1, 1 R2. One over half alpha beta minus beta. And likewise, Heitler and London proposed that there could also be a triplet state. In the triplet state, what happens is you left with 1 minus S. I'll define S. You haven't asked me what S is. I'll define S in a minute. Then you have 1 R1, 2 R2 minus 2 R1, 1 R2 combined with one of the triplets, alpha alpha, beta beta, or alpha beta plus beta. So these are called the Heitler-London quantum states, or the Heitler-London wave functions. You see, the first state is, both of these states are symmetric, anti-symmetric under exchange. This is anti-symmetric, this is symmetric. Right? So if I interchange the two electrons, which means at position R1 I bring the second electron, so I get this term. So this is even under exchange. Okay? If I just had this thing over here, this would be neither even nor odd, because then I would have 2 R1, 1 R2, which is unrelated to the original. So I need to have this linear combination. So this is the singlet state, and this is the triplet state. Now we need to find out, now we have the concept of singlet and triplet because we have 2 electrons. A bond is to be formed, and a covalent bond is to be formed, and that bond means that the electrons could occupy one of these states. So the electrons could be either in the singlet state or in the triplet state. And we would like to find out what is the lower energy state. Whether the electrons in the hydrogen molecule, when they form a bond, whether they are parallel or anti-parallel. In the helium atom, we saw that the triplet state was the low energy state because J was positive for the helium atom. What is the case for the hydrogen molecule? Yes, Shakti.
So why does the whole wave function have to be anti-symmetric?
Because we are exchanging electrons. Electrons are fermions. So that's the symmetrization postulate. So now what we would like to do, we would like to find out the energies of the singlet. Yes.
So should we write first the Hamiltonian for the hydrogen?
Molecule, yes.
Should we, and if we check whether this is the eigenstate of
Yes, we can do that.
it will work out.
Yeah. So this S that you find over here is O squared. And it's given by, this is like a double overlap. This is phi 2 R1 phi 1 R2 or if you want to write it like this. Write it like this. 2 R1 1 R2 2 R2 1 R2. So this is S. It's a double overlapping technique. See, you have stage 2 here, but different coordinates. So this is like an exchanging technique. It's a double overlapping technique, and it's a square of O square. O, as you know, was defined in the following fashion. O was defined as 1 R 2 R. O was defined for a single electron. Now if you take the inner product of this thing with this thing, and take the inner product of this thing with this thing, you get O squared. Alright? So this is our definition of S. Now we would like to find out the energies. Now at this stage, I would like to work in terms of wave function. So I would like to project everything in terms of in the position space. So what I'm interested in finding is the energy of the singlet state. You see, my math is far poorer than yours. So if I can do this, you should be also able to do this. It's just long, tedious, sweaty calculation with an uninterrupted mind, with all your social media links broken for a few hours. You need to do this. There's no way around it. There's no shortcut. Okay, so I woke up at 3 and performed this calculation. You could also do the same. So the energy of the singlet state is given by the Hamiltonian for the molecule expectation value of the energy, which is psi singlet psi singlet, and you need to do some normalization as well. You might need to do it, right? So this is the energy for the singlet state. Likewise, I can have the energy for the triplet state. So this just becomes replaced. Now let's write down the Hamiltonian for the electron, the molecule. The Hamiltonian for the molecule is a pleasant exercise to do. Once again, we have 2 electrons, so we have P1 square over 2m minus E square 4 pi epsilon naught. 1 electron, electron number 1 associated with nucleus A. So we have one term for this. For shorthand, I write this is R1A. Plus P2 square, the second electron, its attraction with nucleus B. Plus or minus 1 electron's attraction with the other nucleus, 4 pi epsilon naught R1B, minus the other electron's association or attraction to the first R2A, to the first nucleus, plus the repulsion between the 2 electrons. Let's call this R12, plus the repulsion between the 2 nuclei. Let's call this capital R. So this is the complete Hamiltonian for the system. Now if you notice, this term is valid, this is a pure atomic Hamiltonian for 1 electron, H atom 1. If you notice, this term over here is the pure atomic Hamiltonian for the second atom, nucleus plus electron, right? And all of these are correlation terms. This, by the way, the internuclear term is a kind of bias. It appears both in the singlet and in the triplet state. Let's call all of this H prime. Now if you insert these values in here, you should be able to find out the singlet and the triplet states. Okay? And if I were to insert these values, it's just algebra, just algebra. I get the following. E singlet is E1 plus x plus j dash 1 plus s and E triplet is 2E1 plus x minus g dash 1 minus s. Alright, so this is algebra. Now I need to define x and j dash. These must be integrals of some kind. I've already defined s. S is this integral over here. Right? Remember, if you would like to compute this integral, this is d cube r1 r1 2 r1 1 D2 R2 R 2 1 R2 2. This is this integral over here. Remember that these are real functions, so taking the complex conjugate is the same. These are real functions. So each one of these terms is an integral. E1 is just the ground state energy of a single hydrogen atom, minus 13.6 electron volt. Now you have 2 electrons, so this just represents the terms that pop out from these atomic, bare atomic Hamiltonians. And we have 2 electrons, so we have 2 hydrogen atoms in a way, inside the hydrogen molecule. So these terms represent 2 times minus 13.6 electron volt. This is minus 13.6 electron volts. Now we have these additional terms over here. S is the double overlap integral. X, by the way, represents this. X is this integral. This is one R1 2 R2 H prime one R 2 R. So first, this is the first electron here, the first electron is here. So if you notice, this is given by D2 R1, D2 R2, R1 1 modulus squared R alright, sorry. Now we have H prime over here. H prime are, all of these are Coulombic terms. These are Coulombic terms that are outside the atom. So one electron is at position R1, but its attraction to the other nucleus. So this is another Coulombic term. This is also another Coulombic term. This is the repulsion between the 2 electrons. This is the repulsion between the 2 nuclei. So all of this represents a Coulombic energy, a classic Coulombic energy. Okay? See, it makes sense. This term along with this term gives you 1 or R1 1 modulus squared, right? This term along with this term gives you R2 2 modulus squared. Then you have all the terms over here, E squared minus E squared 4 pi epsilon naught R1b minus E squared 4 pi epsilon naught R2a plus E squared 4 pi epsilon naught R12 plus E squared 4 pi epsilon naught capital R. And you're integrating all of this over the entire volume. This is what X is. All of these are Coulombic terms. These are charge densities. The charge density for electron number 1, position R1, state 1. The charge density for electron number 2 attached to the other nucleus and its charge density, right, at position R2. So this represents a Coulombic term. It has a classical explanation. However, the term that we have over here, J dash, is a purely exchange term. And if you look at this term, this is given by 1R1, 2R2, sandwiching H prime, 1R2, 2R1. Sorry. 2R1, 1R2. Now this connects first electron position R1 connected to nucleus 1. First electron position R1 connected to the other nucleus. So this connects terms of this kind. This has no classical explanation. This is like an exchanging tensor. Now if you subtract these energies, it turns out that the singlet state is in lower energy. Okay? So if I subtract out these energies, delta E, I can find out the relative energies, the triplet minus the singlet energies. This turns out to be positive, which means that the singlet is now lower in energy. And this equals two x f minus 2j prime 1 minus s squared. So now what we have is this factor, this exchange integral determines the energy splitting. So now you have a singlet state that's lower in energy and a triplet state which is 3-4 degenerate, which is higher in energy, and the energy separation between these states is given by this. And you can say that this equals 2 times J. With J, why do we like to have an energy splitting between singlet and triplet of this kind, 2J? Why do we like to call it 2J? Because we talked about the Heisenberg-Hamiltonian. The Heisenberg-Hamiltonian is of the form 2J S1 or S2. So if you were to express this energy splitting between the singlet and triplet in terms of the Heisenberg-Hamiltonian, which is given by 2J S1 dotted with S2, we would like to call this all of this equal to 2J. This is just a convention. So this energy separation is 2J. And now the singlet is lower in energy because it turns out that J is negative. J is now negative. It turns out that this will lead to an energy, lower energy for the singlet state. For the helium atom, it was the other way around. So depending upon the sign of J, you can get ferromagnetic or antiferromagnetic alignment. It all depends upon the sign of J. So even in molecules, the spin has an important role to play. Whenever a bond is formed, the electrons prefer to be in the singlet state. So in a hydrogen molecule, the two electrons that are forming a covalent bond, their spins are anti-aligned with respect to one another. Without that, a bond cannot be formed. This energy separation is equal to the dissociation energy of the hydrogen molecule. So the molecule will dissociate and it will become separate atoms. So whenever a bond is formed, the spin plays an extremely important role. And how do we construct solids out of these molecules? Once again, the exchange interaction, the value of J is important. If it's positive or negative, that will give you one kind of spin ordering, and there will be separation between the two kinds of spin manifolds. Now in the next lecture, what we're going to do is we've already seen the Heisenberg Hamiltonian, we're going to see the other toy Hamiltonian, which is called the Hubbard Hamiltonian, and we're going to solve all of this, the helium nucleus, the helium atom and the hydrogen molecule, using our toy models, and it becomes much easier. And then we'll move on to real solids from there. So do submit your homework in the next few hours, please. And I'll prepare a new homework and we're going to upload it possibly today, inshallah.